아, 네, 이번 시간에는 분자 분광학의 어떻게 보면 꽃이라고 말씀드릴 수가 있는데요. NMR, Nuclear Magnetic Resonance Spectroscopy에 대해서 배워보도록 하겠습니다. 제가 왜 이 NMR을 이제 분자 분광학법의 꽃이라고 말씀을 드리냐면은, 기존에 배웠던 우리가 분자 분광학 방법들이 어떤 것들이 있었냐면 UV-B스가 있었고, IR 있었고, 라만 있었죠. 근데 그것들이 이제 줄 수 있는 정보는 예를 들면 UV-B스 같은 경우에는 대략 roughly 어떤 화학 구조를 가지고 있다. 그냥 큰 구조를 알아낼 수가 있었고요. 그리고 IR이나 라만 같은 경우에는 그 특정 분자의 어떤 바이브레이셔널 에너지를 알 수 있는 것이기 때문에 특정한 화학 결합, 어떤 결합을 가지고 있는지, 카본 번드를 가지고 있는지, 카본 옥시전 더블 본드를 가지고 있는지 이런 것들을 알 수 있는 그런 정보인데 반해서 NMR 같은 경우에는 특히 유기화합물에 대해서 주로 뭐 탄소나 수소 이런 것들로 이루어진 유기화합물에 대해서 정확한 구조를 줄 수 있는, 물론 이제 IR이나 UV-B스가 함께 있어야 보다 정확한 구조를 알 수가 있긴 하지만 NMR 같은 경우에는 아주 구체적인 정보들, 어떤 카본에 예를 들면 수소가 몇 개 붙어 있고 어떻게 붙어 있는지 이런 정보를 줄 수가 있기 때문에 가장 이제 분자 분광의 꽃이라고 말씀드릴 수 있고, 다른 이제 여러 가지 우리가 앞에서 배웠던 여러 가지 테크닉들과 함께 결합이 된다면 미지의 시료가 있다 하더라도 우리가 그 시료가 어떤 시료인지를 구체적으로 알아낼 수가 있겠죠. 그래서 이제 앞으로 여러분들이 뭐 나중에 예시나 뭐 시험 문제 같은 데서도 보시겠지만 여러 가지 데이터들을 주고 UV-B스, IR, MES, 뭐 NMR 다 준 다음에 이제 화학 구조를 맞추는 거죠. 분자식을 예를 들면 준 다음에 여러 가지 한 분자식에 대해서도 여러 가지 구조가 가능하겠지만 특히 어떤 구조를 가지고 있는지 주어진 정보들을 바탕으로 해서 우리가 알 수 있는 것이죠. 오케이? 그리고 특히 이제 NMR 같은 경우에는 이제 앞에서 봤던 것과 많은 차이가 있는 게, 제목에 보시면 아시겠지만 Nuclear Magnetic Resonance라고 되어 있죠. 앞에서 우리가 다뤘던 이제 UV-B스나 IR, 뭐 라만 전부 다 뭔가 전자가 excitation 되는, 뭐 일렉트론이 excitation 됐든, 바이브레이션 excitation 됐든 전자에 대한 내용이었는데, 이거 같은 경우는 이제 뉴클리어죠. 원자 핵. 전자가 아니라 원자 핵이 뭔가 바뀌는 것. 원자 핵이 어떻게 뭔가 우리에게 유용한 정보를 줄 수 있는지, 그런 것에 대해서 그런 것을 활용해서 우리가 NMR 스펙트로스코피를 활용하게 됩니다. 오케이? 그래서 좀 더 구체적인 NMR이 도대체 무엇이며 어떤 원리로서 작동하는 것이고, 수많은 예들을 통해서 어떻게 그러면 우리가 화학 구조를 알아낼 수 있는지 살펴보도록 하겠습니다. Okay, so as you recall this diagram of different wavelengths or the energy of different electromagnetic radiation, as you see, depending on the wavelengths or depending on the energy or frequency, it spans a wide range of kinds of radiation. Especially for NMR, we are using this radio frequency, very long wavelengths of light. Okay? So what is exactly NMR? As the name indicates, it is basically nuclear thing. It's the effect of nuclear, atomic nucleus effect, especially under magnetic field. Okay? So, if you recall the quantum mechanics or general chemistry class, electrons or nucleus, let's just say this is nucleus, they spin, right? And spinning object behaves such as magnet, right? Since they are moving continuously, spinning by themselves, they act like magnet. Okay? Nucleus, atomic nucleus also spins. Okay? They behave like small magnets. Okay? So if you apply very strong magnetic field, depending on the orientation, depending on the direction of spin, depending on the orientation of small magnets, they are affected by external magnetic field differently, right? That's obvious, right? This direction of magnet and this direction of magnet should be affected oppositely against a strong external magnetic field. So, the energy level of nucleus, let's say that this is energy level of nucleus, they split into two different energy levels under strong magnetic field. That's the main origin of nuclear magnetic resonance spectroscopy. Okay? So, by applying like radio frequency radiation, we are basically measuring this absorption or emission of splitted atomic nucleus energy levels. Okay? That's the main origin of nuclear magnetic resonance spectroscopy. Alright. Very simple, right? Basically uses the spinning motion of nucleus. Things that can be learned from NMR data. If we have NMR data, we can have various information such as chemical structure, 3D structure, molecular motion, etc., etc. So that's why NMR is very useful tool to elucidate the chemical structures of compounds. So if you review the history of NMR, so back in 1920s to 30s, physics begins to grasp the concept of spin, electron or nuclear spin. Okay. And after that, a few scientists studied the NMR, the nuclear magnetic resonance, and Nobel Prize in Physics were given to those scientists, including Purcell and Bloch. Okay. And the interesting thing about this NMR is multiple Nobel Prize has been awarded to related areas of NMR. NMR is that important, right? For first time as Nobel Prize to the study of fundamental knowledge of NMR, Nobel Prize to an application of NMR, FT and 2D NMR, Nobel Prize to, not quite sure about this, but Nobel Prize to, even in medicine, awarded to the development of MRI. You know MRI what? You know what MRI is, right? MRI is a kind of NMR spectroscopy. Okay, that's that important. NMR is that important. Okay, so as I already explained, nuclear magnetism, the spinning nucleus act pretty much like very small magnets. Okay, so they act like magnets. So under very strong magnetic field, they behave like magnets. They split into two different energy levels. Something like this. So depending on the direction of spin, direction of the magnets, they behave differently against the external strong magnetic field. Okay, so it's shown here, right? So this kind of energy splitting under strong magnetic field is called Zeeman splitting. You might recall this from the background correction, Zeeman correction, right? So we used magnetic field to split energy levels, right? That's basically the same. So under very strong magnetic field, energy level of nucleus split into two different levels, and basically we measure this energy difference. Okay. So that's pretty much it. There are more details about like spin and etc. etc. But it's not. I think that's not that important. And one thing to note about this Zeeman splitting is that the energy difference by this external magnetic field here is proportional to the strength of magnetic field. So the stronger magnetic field is, the larger the energy difference is, energy gaps are, okay? So there are many elements that can be accessible by NMR technique depending on their spin, their nuclear spin. We can use various kinds of NMR, and most common NMR is hydrogen NMR, carbon NMR, fluorine NMR, etc. Mostly like hydrogen. Okay. So there are several nucleus which are most widely used as NMR, mostly just hydrogen. Okay. They have spin number of 1/2. Okay. Similarly, carbon, fluorine, etc. Alright. So there are different kinds of NMR. First, or continuous, you can just read. Alright, so this shows the typical NMR spectra. Okay, so this is the NMR spectra of ethanol, CH3, CH2OH. Okay. As you see, y-axis is absorption, basically absorption between these two energy state, right? Y-axis, x-axis is magnetic field. Okay, so as you see, this is the hydrogen 1 NMR. So basically, we are measuring the energy splitting of these hydrogen atoms from OH, from CH2, from CH3. Okay. So if you look at roughly the absorption behavior as a function of magnetic field for various kinds of hydrogen, they show peaks at different position, right? So basically, which means that they behave differently under magnetic field, right? This H, this H, and this H, they behave differently. Okay? Their shift are different, right? As a function of magnetic field. So that kind of difference in shift is called chemical shift. Okay? And here shows the low resolution NMR and in comparison high resolution NMR for the same compound. As you see, this high resolution NMR shows much sharper peaks, even multiple peaks compared to this, right? What is exactly the difference between these two? Okay, we'll also learn about this later. Okay, the first thing to know is depending on the type of nucleus, hydrogen, they show different chemical shift. They are affected differently under magnetic field. Why? Okay, we first need to understand why. Why there is chemical shift. Okay, the reason why is because there are electrons around a nucleus. All the nucleus has electrons or orbital around nucleus, right? Electrons are also charged, right? Electrons are negatively charged, right? Okay. So under very strong magnetic field, so here shows the nucleus, electrons around it, okay? Under very strong magnetic field, electrons are charged particles. They move, they spin basically under this magnetic field because they are charged particles. And by those spinning motion, they induce another field, another magnetic field. Okay? You remember from physics class, general physics class, that right, the moving current, moving electron particles generates magnetic field, right? Okay. So if I explain again, under strong magnetic field, charged particles, electrons move, they spin, and by those spinning motion, they make another magnetic field. Okay, and that field basically reduces the initial external magnetic field. They oppose the initial magnetic field. Okay, which means that if there are more electrons around nucleus, they reduce the external magnetic field more, right? If there are less electrons, less shielding of external magnetic field. So we call that kind of the induced magnetic field by moving electrons as shielding. Okay, because they shield external magnetic field. They shield basically the effect of external magnetic field to the nucleus. Okay? Alright. Alright. So if you recall, nucleus, external magnetic field, and because there are a lot of electrons, this external magnetic field make the electrons move, spin basically, and that spinning basically induce another magnetic field, which basically reduce the external magnetic field. Okay, so the effective field would be the applied magnetic field by the instrument minus some amount, and that this effect is made by these electrons surrounding the nucleus. Okay, and this effect is affected by electron density, how many electrons are there around nucleus, and how they are distributed around nucleus, spatial distribution. If the electrons are close to nucleus, if they are far apart, like delocalized around the nucleus, etc. Okay, so this kind of shielding effect or chemical shift are expressed in terms of ppm, because that change is very small. So we express it as 10 to 6 times nu x minus nu reference. So we are basically measuring the change of this shift as a function of reference, and since that change is very small, we just multiply by 10 to 6 and we just plot this change as NMR spectra. Okay? You might not understand in detail, so let's see some example. Alright. Okay. So here shows the different chemical shifts of different hydrogen at different environment. Okay, so if you look at the x-axis, it is shown as ppm. Okay, and there is some compound which is called trimethylsilane. So trimethylsilane, use the pen here. So here is trimethylsilane, or we call it TMS. Trimethylsilane has chemical structure of CH3 4 Si. Okay. So this TMS, so especially this silicon atom, has much lower electronegativity compared to most other atoms. Okay? So the shielding effect by this silicon atom, shielding effect is really small compared to other atoms. Okay? Oh, I'm sorry. Shielding effect is really large compared to other atoms. Okay? So we use this TMS material as the reference as here, 0. Okay? So we use TMS as a reference point for NMR spectrum. Okay? Because silicon atom has much lower electronegativity, okay, compared to most other atoms. Okay, silicon. So we set this 0 ppm as TMS material and try to check the chemical shift of various kinds of hydrogen, all different kinds, right? At different environment, at different chemical environment. There are many different hydrogen here, all attached to different chemical moieties, right? And as you see, they show different chemical shift. So from here, this kind of hydrogen is shifted to like 2 ppm, this hydrogen like 5 ppm, this hydrogen more 8 ppm, this hydrogen like 10 ppm, much more. Okay? And I mentioned that this kind of chemical shifts are from shielding effect, shielding by electrons around nucleus, right? So if there are more electrons around nucleus, shielding should be larger, right? Okay? So that's why TMS has very large shielding, because silicon is much less electronegative compared to most other atoms. Okay? Let's see the opposite. For example, this hydrogen atom attached to oxygen. Oxygen is quite electronegative, right? So oxygen really likes electrons. Okay? Similar here, CO or 2 oxygens. So let me use the whiteboard. Okay? So this NMR spectra basically shows as a function of ppm. No arrow. So we set 0 ppm for TMS. Okay? Some compounds around here with high ppm, high chemical shift, such as RCO, carboxylic acid, this hydrogen. This hydrogen is attached to carboxylic group, COO. These atoms are really electronegative, right? They really like electrons. They try to take electrons out from the hydrogen, which means that there are not many electrons around hydrogen atom, because these atoms just took hydrogen, electron clouds from hydrogen, right? Since there are not many electrons around hydrogen, this hydrogen atom is more affected by external magnetic field. Since they are more affected, the chemical shift is large. Okay, or we call it, we are calling this region the shielding. Basically, there is no shielding effect because these atoms took the electron clouds from this hydrogen. Okay, so high ppm or high chemical shift hydrogen atoms, okay, shows basically this shielding effect, or we also call it downfield effect. Okay. On the other hand, if there are more electrons around nucleus, for example, like our H, something like that, or whatever. Yeah. This hydrogen atom, there are basically carbon atoms here. Carbon and hydrogen have pretty much the same electronegativity, right? Okay, so there are much more electrons around this hydrogen atom compared to this. Okay, so this hydrogen atom is much less affected by external magnetic field. So the shift, chemical shift, is much small. Okay, so this direction we call it shielding, because this atom is much more affected, shielded by electrons around it. Okay, also we call it off-field. Okay, very simple, right? So depending on the chemical environment that this specific hydrogen have, what kind of atoms are attached to it, okay, that determines the chemical shift. If there are atoms attached with highly electronegative ones, the chemical shift is much large, or the deshielding effect is much large. Okay. Okay. It's pretty simple, right? Sorry. Not quite easy to make. All right. So here shows the example. So here shows the relative chemical shift as a function of electronegativity attached to the CH3X compound. So depending on X, if the electronegativity of this X atom increases, chemical shift increases, right? They have positive correlation, right? So for example, for this compound CH3X, for this compound, if X is halogen atom, so if the X is, where is the cursor? Sorry. Okay. If the X is iodine I, CH3I, the chemical shift is 2.16. If X is bromine, Br, chemical shift is 2.68, or a little larger, because bromine is more electronegative than iodine. For Cl, chlorine 3.05, for fluorine 4.26. Okay, as the electronegativity increases from iodine, bromine, chlorine, fluoride, they increase the chemical shift. Okay, but there are some chemical shifts that we cannot really understand. For example, if you check the chemical shift, chemical shift of different hydrogen, alkane, or alkyne, Okay. If you compare the chemical shifts of these three different hydrogens, the chemical shift is 0.9 for this hydrogen, but for alkene 5.8, much larger. That's very weird, right? But for alkyne 2.9. Why? That's very weird, right? Also, for aldehyde, RCHO, chemical shift is about 10, really large. Okay. For benzene, chemical shift is about 7.3. Also very large. Why is it? Okay. If you only care about electronegativity of all same carbon should be same, but chemical shift is really different. Also same for here. Why is it so different? Okay, we need to understand this. There is another effect. Okay. All right. There is another effect. So, for example, for benzene or for carbonic compound, so for benzene or for compound with double bond, CC double bond or CO double bond, okay, they have another effect. Basically, benzene ring or double bond have pi orbital, right? Pi orbital, okay, on top and below this ring. And if there are external magnetic field, this pi orbital or the electrons comprising pi orbital, they move. They basically form ring current. They flow, forming ring. Okay? And ring current induces another magnetic field, right? And because of this ring, actually the direction is wrong in this textbook. The direction is this way. Sorry. So direction is this way. Okay. Same as this. Okay. If the direction of ring current is like this, the direction of induced magnetic field is in this way. And because of this way, there's magnetic field around this ring like this. Like this, like this, like this. Okay? In this direction. Basically in this direction. Okay? So, the hydrogen atom attached to benzene ring or hydrogen atom attached to carbon-carbon or carbon-oxygen double bond, they experience another magnetic field which is in the same direction as the external magnetic field. Okay? Same for these two cases. That's why hydrogen atom attached to benzene or hydrogen atom attached to double bond has much larger chemical shift compared to other compounds. Okay? How about triple bond? Carbon-carbon triple bond. Okay? Carbon-carbon triple bond also have pi orbitals around it. Okay? But the problem is, since there are two different pi orbitals for triple bond, right? The pi electrons around this triple bond are basically symmetric. So they, under external magnetic field, they form ring current, something like this. Okay. So ring current is in this way. So the magnetic field is in opposite direction to the external magnetic field. Okay, that's why carbon-carbon triple bond, the hydrogen atom attached to triple bond shows less chemical shift than other atoms. Okay? Compared to, for example, like carbon-carbon double bond. Okay? Alright. So if I summarize, there are several chemical groups which are more de-shielding. For example, atoms with high electronegativity, such as halogen atoms, right? Also, benzene ring, carbon-carbon double bond, carbon-oxygen double bond. Those are chemical groups which are more de-shielding or which induce more chemical shift. Okay? Here shows the two NMR spectra of the same compound under different magnetic field. Okay, as you see, as the magnetic field increases, the chemical shift increases, right? You can clearly see the difference between these two spectra. But the interesting thing is there are multiple peaks, right? Multiple peaks, 4 peaks here, 3 peaks here. And there are the gaps between these small peaks are same regardless of the strength of magnetic field. Why? Although the chemical shift is different, these small gaps are pretty much same. Why? Okay. So here shows the different chemical shifts of the different chemical moieties, functionalities. Okay. Okay. So I want to explain this first. Okay. So let's move back. So if you recall the NMR spectra under low resolution and high resolution of the ethanol, at low resolution we could not really see the fine structure. We could only see broad peaks. But here we could see multiple peaks. 1 peak here, 4 peaks here, 3 peaks here. Why? Why there are multiple peaks for same hydrogen? For OH there are 1 peak. For CH2 there are 4 peaks. For CH3 there are 3 peaks. Why? That's because of there are. Oh, sorry. This is the some examples. Let me just first explain the J coupling first. Okay. So. Sorry. Okay. The reason why there are multiple peaks are because of J coupling. J coupling is a kind of through bond interactions. Nucleus have spins, right? And spin of that nucleus affect the spins of the electrons around it. Okay? And that electrons also affect the spin of the nucleus next to it. Okay? So basically, nucleus, closely located nucleus affect each other. That's why they split energy. Okay? So let's say that. Let's just see an example just based on the previous spectra of ethanol. So ethanol have molecular formula of OH, CH2, CH3. There are 3 different kinds of hydrogen. Okay? There are two hydrogens here, 3 hydrogens here. And under magnetic field, okay? Not on the magnetic field, actually. These 2 hydrogens, each hydrogen is magnets, small magnets. They have spins. So there are 2 hydrogens. Each hydrogen can have 2 different spins, upfield or downfield. And two hydrogens can have this spin, this spin, this spin. Four different combination of spins, right? Okay? And this spin, these two are same basically, this spin. All these three different kinds of combination of spins are affected differently by magnetic field. Okay? Also external magnetic field, also by neighboring nucleus, because each hydrogen atoms are small magnets. Okay? So they affect each other. Okay? How about three atoms? Each hydrogen atom have two different spins. So there are multiple combinations possible, such as total up field, up, up, down, up, down, up, up, down, down, up, 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 down, 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 up, down, 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 up, or all down. So there are basically four different kinds of combination as 1, 3, 3, 1 ratio. Here 1, 2, 1 ratio. Okay? So these three hydrogen atoms affect neighboring hydrogen or nucleus differently depending on their spins. These two hydrogens affect neighboring hydrogen since they have different spins. They have different combination of spins. Okay? So this is why in high resolution NMR spectroscopy we see a lot of different peaks. Okay? Alright. Okay. So here shows this is not important. Okay. So let's just see some simple example. So if you look at the textbook, page 518, there are some rules to check this like J coupling or through bond interactions. So rule number 1, let's just write it down to the whiteboard. Okay. If you look at the textbook, page 515, there are rules about this J coupling. The first rule is that equivalent, basically same nuclei do not interact each other. Sorry. First rule. Second rule is that as the distance between nuclei increases, the coupling, the interaction, decreases. So in most cases, we only measure the J coupling between the neighboring nucleus. Number 3, multiplicity is n plus 1. I'm going to explain again. 4 multiplicity is Na plus 1 times Nc plus 1. Here N is the number of hydrogen atoms. Okay. Okay, and number 5, relative peak area. Relative peak area follows Pascal's triangle. And importantly, this J coupling is independent of external magnetic field. Okay? You remember that I explained that the energy gaps between these small peaks are basically same at different magnetic field. Okay? Alright. So here, multiplicity means number of peaks. How many peaks are there for specific kinds of nucleus or hydrogen? Okay? So multiplicity is n plus 1. N is the number of hydrogen atoms next to it. Okay? For example, if there are 3 carbon, Ca, Cb, Cc, and multiplicity of carbon B here, basically for example, if there is hydrogen here, is multiplication of Na, number of hydrogen atoms attached to carbon A, number of hydrogen atoms attached to carbon C. Okay, so it might be a bit might look complicated, but it's very simple actually. Let's see some example. So if you look at the example 19-3 in the textbook, so there are multiple compounds. First one is Cl, CH2, 3, Cl. So if you write down CCCl, so it looks like this. Okay. If you recall the first rule, equivalent nuclei do not interact with each other. Okay. If you compare this atom and this atom, they are basically same, right? They are basically in the same environment, right? If you rotate it, it's basically same. Also, these two are also same as these 2 hydrogen atoms. So all these 4 hydrogen atoms are equivalent. They do not interact with one another. Okay? But these 2 hydrogens they are equivalent to each other, but they are different from these 4 hydrogens, right? Okay? Alright. So basically in this compound there are 2 different kinds of hydrogen. This hydrogen and this hydrogen. Okay? Let's say that this is hydrogen alpha and this is hydrogen beta. And let's calculate how many peaks, how many NMR peaks these hydrogens have. Okay? Okay, first, alpha hydrogen. Alpha 1. There are 4 hydrogens. Let's first calculate multiplicity. How many peaks, multiplicity, how many peaks would these alpha hydrogens have? Multiplicity is n plus 1, right? N is the number of hydrogen atoms next to it, next to alpha. So, this is basically alpha, this is beta. So there are 1, 2 hydrogens, right? 2. So multiplicity of alpha hydrogen is 3. Okay, there would be 3 peaks for these hydrogens. How about beta hydrogen? N plus 1. So how many N? 1, 2, 3, 4. 4 N's. So multiplicity of beta hydrogen is 5, right? There will be 5 peaks. And we have 3 peaks. In what ratio? According to rule number 5, we should follow Pascal's triangle, something like this. Okay? Pascal's triangle. If the number of n is 3, the relative peak area is 1 to 1. Okay? 1 to 1. So, these 3 peaks would have a ratio of 1 to 1. You remember why it is 1 to 1, right? 1 to 1. This is why. Okay? Since there are 2 different hydrogens here. Okay? How about when multiplicity is 5? If you look at the table, or Pascal's table, it should be 1, 4, 6, 4, 1. Okay? Very simple, right? Okay. Let's do one more example. Okay. Alright, let's do the second one. H3C, C, CH3Br, right? You first need to check how many different hydrogens are present. These 3 hydrogens are basically equivalent. They are also equivalent to this hydrogen. Okay, these 6 hydrogens are equivalent, alpha hydrogen. There are 1 hydrogen which is different. Okay. For alpha hydrogen, multiplicities. There are 1 hydrogen, multiplicity is 2, right? If there is 2 peak, the ratio should be 1-1, according to Pascal's triangle. Okay. How about beta hydrogen? For beta, there are 6 hydrogens, right? So multiplicity is 7. So the ratio should be 1, 6, 15, 20, 15, 6, 1. Right? Very simple. Right? Okay. Okay. Good. Okay. All right. But the problem is there are always exceptions. Let me briefly explain the exception. We used rule n+1 for multiplicity. That rule can only be applied if the coupling is same for equivalent atoms. If it is different for different hydrogen, then we cannot use n+1 rule. For example, let's see some compound of alkene. Let's say we have 1 hydrogen and they will have 1 peak, right? If there is another hydrogen, they affect each other. Okay? Since there is only 1 hydrogen, multiplicity is 2, 1 to 1. Right? And this difference is made by this hydrogen. Okay? Okay. Up to here is simple. But what if there are another hydrogen A and hydrogen B? Okay. This hydrogen and this hydrogen is not equivalent to this hydrogen, so they affect differently. Okay, and in this case we have to do the effect separately. So first, hydrogen A affect hydrogen, this hydrogen, so they have double it, and hydrogen B affect these peaks. Okay, so these peaks also separately at this position shows doubling, something like this. Okay, so this shift is made by hydrogen A, this shift is made by hydrogen B. So we're saying if we have another hydrogen, hydrogen C, B, okay, then they show another splitting, something like this. Okay, it's different from the previous n+1 rule. Okay, this rule is applied when the equivalent hydrogens are present, but in this case they are not equivalent, right? So you have to differentiate between these two different cases. Okay, then let's move back and solve some examples. Okay, all right. We have some examples to understand the basic concept of this NMR. Okay. 오케이. 우리 지난 시간에는 이제 NMR 이 기본적인 원리하고 몇 가지 기본적으로 알아야 되는 사항들, NMR이 이제 어떤 이제 분석 방법이며 또 어떠한 원리에 의해서 그런 픽의 차이가 나타나는지, 케미컬 시프트랄지, J 커플링이랄지 이런 것들 우리가 기본적인 내용들을 다뤄봤었는데요. 아직 많은 예를 다뤄보지는 못해가지고 일단 우리가 지난 기본적으로 배웠던 내용들을 이해할 수 있는 그런 예제를 한번 보시고, 이 강의 노트를 보시면은 그 뒤에는 굉장히 많은 이제 NMR들이 NMR 스펙트라가 나와 있죠. 그래서 그걸 통해서 실제 이제 연습을 많이 해보는 거죠. 어떤 화학물질, 어떤 유기화합물은 어떠한 형태의 NMR을 가질 것이다. 또는 반대로 그 NMR 데이터를 봤을 때 이 구조가 어떤 구조일 것이다. 이런 거를 예측할 수 있도록 굉장히 많은 연습이 필요합니다. 사실. Okay. So let's take some example. The first problem. Circle the proton that is more shielded. Okay. If you recall the shielding, more shielded hydrogen should be attached to the atom which is less electronegative, right? Okay. So the protons which are more shielded is carbon, the hydrogen attached to carbon, right? Because nitrogen is more electronegative compared to carbon, right? Which of the following atoms has the lowest electronegativity? We first understand what electronegativity is, right? So, like atoms with higher electronegativity is usually like halogen atoms, right? So, lowest electronegativity atom is among these. You can clearly see that it is carbon. Oh no, phosphorus. Okay, sorry. Right? So phosphorus is as you go down from the periodic table, electronegativity decreases, right? Which of the following attaching protons will have the highest electron density? So if the hydrogen has highest electron density, which means that it is more shielded, right? So if you compare these 5, the most shielded one should be this one, because phosphorus has lowest electronegativity, right? Which of the following attaching protons is the most shielded? Basically same expression, right? Same. Shielded, highest electron density. Most deshielded should be the opposite case, okay, with the highest electronegativity, which will be fluorine, right? Which of the following attaching proton has the lowest chemical shift? If the chemical shift is low, which means it is more shielded, Okay, same expression. Phosphorus, which with following attaching protons has the highest chemical shift, which is more d-shielded. This one. Rank the following molecules in the order of the one with the most d-shielding protons to the one with least d-shielded protons. Most d-shielded one, which means highest chemical shift, right? For these carbons. Okay, so it should be this one, right? More shielded compared to least shielded. Because there are, I'm sorry. Oh, I think this is wrong. So just ignore this problem 8. Something's weird. 3, 2. I'm not quite sure about this. Okay. So let's just ignore this problem. Fill in the blank. Higher electronegativity of the atom that proton is attached to. The electron density at the proton is lower because it is higher electronegativity, and proton is more less shielded because proton has a higher chemical shift, right? Higher, okay, right? Because this is atom is more electronegative, right? So it should be shifted more. Circle the proton that is least shielded, or d-shielded, right? Which shows highest chemical shift, right? Which should be this one, because this is attached to a highly electronegative oxygen atom, right? Okay. As you remember, this proton has like very high chemical shift of about like 10, right? Compared to other hydrogens. Okay, so here shows the NMR spectrometer design. Basically, we need strong magnets. Okay, something like it's something like this. So there are very strong magnets. So one thing to note is that if you ever use NMR spectrometer, because of these strong magnets, if you take your wallet with you, like near this NMR instrument, the credit card would fail. So you have to put the credit card a certain distance from this machine and just use the instrument. Okay, that's very useful tip. So there are many different applications that we can use using NMR, even in biochemistry area. Okay, so as I mentioned earlier in previous class, that MRI is a kind of NMR technique. So that's why NMR is awarded a Nobel Prize in medicine. Okay? It's very useful. So there are many practices that you can do. So let's review some characteristics of hydrogen NMR. First, number of signals. So first you need to check how many different kinds of hydrogens are present. That determines number of signals. How many different kinds of signals are there. Okay. Second, you need to check the positions or chemical shift of the signal. Okay. You need to check what kind of hydrogens are there. How many, what kind of electronegative atoms are attached, or if there are like carbon-carbon double bond, carbon-oxygen double bond, or like benzene ring, something like that. Relative areas on the signals. Relative areas should be matched to the number of hydrogens. Okay. Also splitting patterns. You need to check the J coupling. How many protons are there attached to the atoms next to it. Okay. The neighboring hydrogens. Okay. You need to check the multiplicity, and you need to check the Pascal's triangle. Okay. So first, number of signals. How many different types of hydrogens in the molecules? Okay, you need to check what hydrogen molecules are equivalent. Okay, let's see some examples. Here, methane, ethane. So for methane, how many different kinds of hydrogens are there? The answer is only one kind, right? So 1. For ethane, 1, same. All 6 hydrogens are equivalent, right? So if you look at example, for cyclohexane, all 16 hydrogens are basically same. So only we can see one signal, one peak. For benzene, 6 hydrogens are all same, all equivalent. 1. For this, also same. For this, there are 2 different kinds. These 4 hydrogens are equivalent, and these 6 hydrogens are equivalent. So you can experience 2 different peaks from this compound, right? Also here, 9 hydrogens are equivalent, so 1 peak. For here, these 3 and these 2 are 2 different kinds, so you will measure 2 different peaks. For here, these, and these are all different, right? So 3 different peaks. These 2 different peaks. Okay. For this compound, this hydrogen, this hydrogen, this hydrogen, and this hydrogen are all different, right? All in different environment. So we will see 4 different peaks. For this, these 2 hydrogens and these 4 hydrogens are same, right? So 2 different peaks. For this, these hydrogens, and these 4 hydrogens are same, basically, right? So 3 different peaks. Okay, so you now know how many peaks are there, how many equivalent hydrogens are there. Okay. Next is chemical shift. What kinds of hydrogens are present? Okay. So you need to pretty much like know the overall like peak positions or chemical shift of different kinds of hydrogens. Primary carbon, about 1, secondary, tertiary carbon is pretty much similar. Aromatic, if there are benzene ring, it's around 6 to 8. Allyl, 1.7, benzyl, 2.2 or 3. If there are halogen atoms, a little bit more chemical shift. Alcohols are pretty like change, depending on the environment. Okay, and also if you recall, carboxylic acid around 9, 10. What else? The carbon-carbon double bond is like about like 6, something like that, 5, 6. So you need to understand the different positions, and reference compound is TMS at S10 ppm. Okay. All right. So for toluene, there are 2 different kinds of hydrogens. These 3 kinds, actually these 5 hydrogens are a bit different, but pretty much same, because this is only CH3. So these 3 hydrogens and these 5 hydrogens are different. So we can expect 2 peaks, right? Okay. And peak positions for these hydrogen. These hydrogens are benzyl hydrogen. So if you look at benzyl, 2.2 to 3, it's about here 2 point something, right? For benzene ring, about 7, right? So you can clearly see the difference between these 2 hydrogens in terms of chemical shift. Okay? You can also check the previous compounds for different chemical shift. Okay. Alright, skip. How about next is integration of relative areas of each peak. Okay. For them, you only need to do the calculate the how many hydrogens are there, how many equivalent hydrogens are there. Okay. For example, for this compound, there are 3 different kinds of hydrogens, right? You can expect 3 peaks, and the relative intensity or area, peak area of each peaks are 3 to 2, right? Because there are 3 hydrogens, 2 hydrogens, and 2 equivalent hydrogens. Okay. Similarly here, there are 2 different kinds of hydrogens. These 6 hydrogens are same. This 1 hydrogen is there, so 6 to 1. Okay. Similarly, you can also do the to the rest of it. Okay. Same thing. Okay. Alright, so you can do this kind of integration or overall peak areas by using the computer program when you measure NMR spectra. Okay. It's not that important. Okay. Also splitting pattern, the J coupling. You can check the first multiplicity n+1, and you can check the Pascal's pattern depending on the multiplicity. Few things to note. This n+1 rule only applies to equivalent neighboring hydrogens. If they are not equivalent, you cannot use it, right? You remember the example that I showed you for the alkene compound, right? Another note is that alcohol hydrogen, OH hydrogen, usually does not split neighboring hydrogen, okay? Nor is it split. So you can pretty much ignore this OH hydrogen. They only show just single peak, single relatively broad peak, okay? And also at various chemical shift. It's not quite sure at what position you can observe this alcohol hydrogen peak, okay? Alright, so this is some example. This is pretty much a very simple one. Okay, for example, this one. There are 3 different kinds of hydrogen, A, B, C, and you can experience 3, 2, 2 peak area. How many peaks? For this hydrogen A, you have 2 hydrogens next to it. Okay, so multiplicity is 3. Okay, you will have 3 peaks as 1-to-1 ratio according to Pascal's triangle. For hydrogen number C, also you have 2 hydrogens, so you will have 3 peaks, triplet. For hydrogen B, there are 5 hydrogens, so you will have 6 peaks, basically very complex one. Okay. How about this one? There are 2 different kinds. These 6 hydrogens are equivalent, and this 1 hydrogen. So these 6 hydrogens have 1 hydrogen's neighbor. Okay, so they have 2 peaks, doublet, and this 1 hydrogen have 6 neighbors. So this hydrogen would have septet or 7 peaks. Okay, it's pretty much like this. So you can do the same thing. All right. So there are many examples, and I think you can do it by yourself. And also, I'm going to do the more examples in the lecture. Okay? This is pretty much very simple examples. Okay, you can do it by yourself and also in the lecture. All right.